the rare and remarkable moment is here. Thrice Atlas passes near Mars. As of October 4th, 2025, the object is drifting away from its closest point to Mars, but still close enough to matter. Just yesterday, on October 3rd, it made its closest approach to Mars from Earth. Imaging is next to impossible right now. The sun's glare dominates this region, and the object is essentially hiding behind it. That makes the spacecraft orbiting and roaming Mars our only real vantage point to watch 3I Atlas for now. Yet, ironically, many NASA websites and feeds have gone silent, affected by a government shutdown at precisely the moment we need real-time updates. Shutting down key public access during an interstellar flyby feels awfully convenient, especially when researchers around the world are eagerly pressing to follow what might be the most unusual object ever seen in our solar system. There's already intense speculation. Some suggest it might be a highly active comet unlike anything we've seen. Others propose more exotic ideas. A probe from beyond the stars, a piece of technology, or an alien craft. Whether those theories are plausible or not, the timing of this blackout raises eyebrows. Fortunately, we may have a lead. On October 2nd, the Perseverance rover imaged a streak across a multi-minute exposure sequence. That streak does not match the normal motion of Mars's sky background. Instead of being vertical or aligned with the star trails caused by Mars's rotation, this path is slanted and consistent across images. It's real, it's not a glitch. It's moving fast. It's plausible to consider that what we saw was 3 Atlas itself. Credit for noting this streak goes to Drew, whose post on Twitter spurred further review. Now, the object's size remains a mystery, but lower limit proposals cluster around 5 km wide, possibly more. It lacks the huge classic dust tail of a comet. Instead, it seems to be cloaked by a vast diffused coma of ionized gas and dust. Its speed is extraordinary, roughly 60 kilometers, accelerating toward a peak near 68 km/s as it nears perihelion. At the end of September, around September 25th, a coronal mass ejection struck 3 Atlas, which may have ionized or energized its surroundings. But follow-up images taken on September 27th and October 2nd show no cataclysmic restructuring, no sudden tail breakoff or fragmentation, only hints of gradual expansion in its envelope. That's why the NASA coverage meant so much to everyone. Thankfully, we are not powerless. Mars Express and Exxon. Mars Trace Gas Orbiter were also lined up to observe 3 Atlas at close approach, capturing imagery and spectral signatures of gas and tail dynamics. The upcoming JUICE mission will intercept the object as it continues toward perihelion. However, sunnier communications will delay much of that data delivery. Together, these assets could stitch a better portrait of 3I Atlas. All eyes are now on ESA, our best hope for new images of 3I Atlas. How big is 3I Atlas? Figuring out how big a comet really is can be difficult. The challenge lies in telling the nucleus apart from the hazy coma around it. As a comet draws closer to the sun, its frozen ices turn directly into gas, dragging streams of dust out into space with them, which forms their distinctive trail or coma. This can make the comet appear far larger and brighter than the solid body itself. A team from Harvard, led by Richard Kluder, R.V. Lobo, and Peter Viz, analyzed observations of 3I Atlas collected between May 15th and September 23rd from 27 different observatories worldwide via the Minor Planet Center. They compared the actual trajectory to the path we'd expect if only gravity acted. What they found was a tiny but noticeable push, less than 15 minutes per day. But comets with active outgassing usually get a slight push from the jets of escaping gas. In 3I Atlas's case, the measured non-gravitational acceleration is surprisingly low relative to the observed outgassing. That suggests the nucleus is heavy enough to resist being pushed around much by those jets. From this, the researchers estimate the comet's core weighs over 33 billion tons, with a diameter of roughly 5 kilometers, not counting the surrounding coma. It appears to be about 3 to 5 orders of magnitude more massive than earlier interstellar. Visitors.Lobo has argued that given what we expect about the available population and heavy element abundance in interstellar space, we should by now have seen far more interstellar objects of modest sizes before stumbling into one so massive. Yet we haven't, and that marks 3I Atlas as a significant outlier. Lobo even entertains a speculative alternative that the object could be of technological origin, citing the unexpectedly large mass, the alignment of its trajectory, and some purported detection of nickel without iron as provocative hints. NASA scientists, however, urge caution. The prevailing view remains that it is most likely a natural object. From images, we also saw that this object is active, which means that around the nucleus there is some coma, an indication that this object is in fact a comet. Meanwhile, some scientists aren't asking what 3Pi Atlas is, but what its purpose might be. Astrophysicist Suzanne Fenner's idea is simple, but striking. 3. My atlas may be a planet-making seed. But how can a wandering rock from another star system spark the birth of an entire planet? Let's take a tour. Enter a young solar system where a new star sits at the center of a great dusty ring. Here, tiny grains of rock swirl like smoke, clumping together into pebbles. With time, they snowball into boulders, and then into planet males, the raw ingredients of planets. Given enough time, these grow massive enough to gather even more material. It sounds straightforward, but as we'll see, there's a serious problem with this picture. Disks only last a few million years before the gas is blown away. That window seems too short to explain how massive planets like Jupiter and Saturn were able to form. Now imagine a different scenario. Into this disk falls an interstellar object, a body already big enough to serve as a ready-made core. Instead of starting from dust grains, the disk suddenly has a solid seed that can immediately start pulling in surrounding gas and material. In this way, an alien traveler could speed up the birth of a new planet. Fenner's simulations support this idea. She found that massive stars are better at capturing interstellar objects than smaller ones. And sure enough, gas giants are more common around bigger stars. The match between theory and observation is striking. If this is true, then interstellar objects like Oumuamua, Borisov, and 3I Atlas aren't just drifters. They may be the sparks that ignite planetary systems. Some might have seeded gas giants in faraway systems. Others may even have played a role in our own solar system's early history. It's a bold idea and still unproven. Just like Lobo's theory, interstellar objects are notoriously difficult to study. They appear suddenly, move quickly, and vanish into the dark. But this time, we're ahead of the curve as we have detected it well in advance. And our technology may finally let us uncover its true nature rather than just guessing after it's gone. The energy required to beam such a transmission across interstellar distances was another clue that disturbed experts. Natural emissions could be dismissed as byproducts of cosmic phenomena, but focused signals demanded technology and intent. Whoever engineered the broadcast wielded power far beyond anything humanity had achieved. To sustain coherence across such a distance required mastery of energy on a scale we could scarcely imagine. This realization drove home a sobering fact. In the cosmic hierarchy, we were the junior species, fumbling with primitive tools, while giants reached across lighter years with precision. The very act of receiving the message underscored our vulnerability, for it showed that others could find us with ease.